Hey students, this is Professor Omelianchuk, and today I'm going to be talking about gates and circuits. So we're going to be starting a new unit. We are now done with derivation hell, so that's a good thing. And today, I just look a little bit about how these slides work. It's actually all one slide set. All right, so even though you follow two different links, they're going to go to the same slide set. So what I'm going to do just in this particular lecture is just introduce the language and particulars of digital circuitry, and then I'll get into how we analyze them and draw them with our normal form that we learned a little while back now. Actually, we've come a long way, and we're going to use normal form to help us out and draw some circuits. All right, so look, at this point in the course, you may be wondering, why do I have to study this? Like, why study logic at all? Like, what is the point? It just seems like a lot of just puzzle solving and pushing symbols around, and this is just becoming kind of tedious. And I think that's a fair feeling, all right? I mean, I don't blame students for feeling that way at all, right? And so what I want to say about why study this class and why it's important and why it's part of a college education is that what we're trying to do here is get you to learn to think very abstractly, especially to kind of discern formal patterns that occur in different languages, whether it be a natural language like English or a formal language like TFL. And we want to learn how to kind of increase our capacity to detect these argument forms that come up and where entailment holds and where it doesn't. Right? That's an important thing, right? It's also about following rules, right? And what I mean by rules here, right, are not like commands or rules of ethics, but rather formal principles of reasoning, right? It's important to follow these because if you don't follow them, then you just act unreasonably and you think unreasonably. Right? And these two things alone have helped me immensely. As an educated person, as a philosopher, I use logic every day in the things that I've learned in this sort of course, and just applying it in how I read and how I write. Okay, it's a big deal, right? How you read and how you write have to do with how you think, and logic is a part of that. It also teaches you to satisfy constraints. We have to operate within certain limits. Okay, this will always be the case no matter what in life. One of the annoying slogans that you'll see around the University of South Carolina campus if you ever go there, these little posters say no limits, right? Our leadership has no limits. And, of course, we nerds in the philosophy department would always just make fun of that and say, well, that's ridiculous. Of course there's limits. Right? And logic is part of what specifies what those limits are. Okay? Now all that's kind of pie in the sky, abstract, the sort of gobbledygook that a logic professor might say. It's all, is there anything specific? Is there anything tangible? And the answer is yes, actually. Now, not every one of you is going to be doing this, okay? But one real world application is the language of digital circuitry, right? And what digital circuitry is the logic of inputs and outputs and how they relate to certain theories of computation. Logic is very much a part of this, right? So let's talk about digital circuits and what the language of digital circuitry entails. First thing you should observe about it is that instead of using T's and F's, it uses ones and zeros, right? So it's a binary system. You can think of the ones as representing on and the zeros as representing off. And that kind of corresponds with the binary languages that we've been looking at that utilize truths and falsehoods. The second thing to know is that circuits are made from gates and wires that connect the gates, right? And they transform one or more zeros and ones into a single zero or one. So you can kind of see here, you have some wires, all right? and you have, right, two of them are going into a gate. And so there's a pattern here, a 0 and a 1. And given that pattern, the gate, then we don't know what kind of gate this is, but what it does is it takes that information and then mechanically spits out a 1. All right, and then of course that's linked up to this other wire here that's a 0. Now you have a 1 and a 0 going into this gate, and then that information is taken as input, and then it outputs a 0. Right, so there's a logic here of input values and output values, right? And so digital circuitry is all about capturing how these things work. What's the connections from the inputs to the outputs? All right, and so that's what we're going to be taking a look at. The other thing too that we can do once we kind of figure out, okay, when you have certain inputs, you're going to get certain outputs. And once you have that information kind of organized, you can put it into a table of operations, right, that specify what the inputs and outputs mean. And so they end up kind of looking a lot like truth tables, right? So here is the familiar TFL connectives in the language of digital circuitry. All I've done is just replace the T's and F's with 1s and 0s here. However, digital circuitry does not make use of arrow formulas, right? So biconditionals and conditionals are not part of the language of digital circuitry. They actually get X'd, right? They get removed from the language, and they're replaced with two other relations. All right, so this one I use a connective here, this little bar that I've been using to kind of draw my subderivations in the slides. It actually has an official name. It's called the Sheffer stroke. What's interesting about the Sheffer stroke is that its table of operations looks like this. If you have a 1 and a 1, you get a 0. Otherwise, you get a 1. So it's actually kind of the opposite, right? It's the negated formula, basically, of a ampersand, right? You kind of see that, how it's negated, right? So the Sheffer stroke is the negation, basically, of the and, all right? And now you might be wondering, well, why introduce that? Could you just use negation and you could, that would work in TFL. What's interesting about the Sheffer stroke, though, is that there are logical languages that only have this symbol and no others, right? So this is like your only connective. And what's interesting is that you can get equivalent formulas or equivalent tables that represent all of these tables of operations using just this. It's quite complicated, and it's not something I can reproduce for you easily in the slides, right? And you might be wondering, well, why would you do that? That seems really kind of hard. Well, what's interesting about that is that it's hard for humans to do, but it's not hard for machines to do. And if the machine only has to keep track of the semantics of one symbol, well, that's a very simple programming language, and it actually ends up being kind of efficient, right? So that's one of the reasons why the Sheffer stroke is involved in the language of digital circuitry. The other thing that we give ourselves is an exclusive OR. So in TFL, we got by with just an inclusive OR, and then we used conjunctions and negations to kind of do our work. The thing is, though, in digital circuitry, that ends up making things more complicated, right? So what digital circuitry designers have done is they've given themselves a connective. Now, I don't have a fancy symbol for you. I just call it XOR, right? That's actually what it's called in the language of digital circuitry. And that means exclusive OR. And so the only time it's ever going to put out a 1 is if only one or only the other is a 1. Okay? If you get 2 1s or 2 0s, it's a 0. Right? So that's the one thing you have to know that's different about digital circuitry. Next thing to say is this, is that you have different gates. And each of the connectives here, so like ampersand, you know, the inclusive OR, the NOT, and the Sheffer stroke, and the XOR, these correspond with gates, and they're pictures. Right now, they're just like the gates that I kind of introduced you on the other slide there, where you have 2 inputs, you know, coming into the gate, and then 1 output coming out. All right, so the thing is that if you get, you know, a 1 and a 1 on this gate, you get a 1. Otherwise, you get a 0, and this is why this is called the AND gate. Okay, the AND gate, it's representing that conjunction relationship. Now, what you need to remember here is the shape, right? The AND gate looks like a horseshoe, right? It's got 2 little right angles, right? So you have to be, this is just another thing you have to remember. You have to remember what these look like, okay? Right? Otherwise, you won't be able to kind of do the problems that I'll assign you. Let's look at the OR gate, right? The OR gate, there you have the two inputs, one output, and it looks like an arrowhead, right? And so it puts out a 1 if and only if, A and B are 1, or A is 1, or B is 1. Otherwise, it puts out a 0. Okay? So just note that it looks like an arrowhead, right? That's the OR gate. The NOT gate's very simple, right? It just takes one line as input, right? And then it inverts what the input is to the output. So if it gets a 1 coming in, then it outputs a 0, or if it gets a 0 on the input, it outputs a 1. Sometimes it's called a bit flipper, right? That's another way of talking about a NOT gate. And it's important to kind of observe what the NOT gate looks like. It's just a little triangle. And notice that it has this little tennis ball type of shape on the tip of it. You'll want to notice that because when we look at the NAND gate, which is the NOT AND gate, that's the Schoeffer stroke, right? The NAND gate looks just like an AND gate, right? It's got the horseshoe at the right angles, okay? But then it has this little tennis ball on the output line. And so you should read that as being the negation of an AND gate, all right? And so that's what the table of operations specifies, right? It'll put out a 0 if both the inputs are 1, otherwise it outputs a 1, okay? So remember that, be able to distinguish that from the AND gate. And then the last gate we want to take a look at is the XOR gate. Notice that it looks like the OR gate because it's got the arrowhead shape. However, it has kind of this extra line here and this gap. And that you got to keep an eye out for, right? Because that distinguishes the XOR gate from the OR gate. And so then you have the 0, 1, 1, 0 pattern rather than 1, 1, 1, 0. All right? All right, so those are the gates. You got to remember what those are and what their table of operations are. Okay, and so I think remembering the table of operations should be pretty easy. You know, these are the two new ones, the NAND gate and the XOR gate. So you just have to kind of keep those straight and be sure to distinguish them from the AND gate and the OR gate. Let's talk about equivalent circuits, right? And why logical equivalence is actually very important in digital circuitry, right? The thing about logical equivalence is and why it's important for producing efficient circuits is that they always produce the same output given the same inputs. All right, so if you have two equivalent circuits, right, and one has a smaller size and a smaller depth, and I'll talk about this on the next couple slides, you're going to have a more efficient circuit, right? That's just how logical equivalence can be useful, right? You want to have the same outputs given the same inputs, right? And so let's just compare the NAND gate, right, in its table of operations, which is going to be 0, 1, 1, 1, with a more complex circuit where we have an AND gate right here. Here you're taking the two inputs, then it's outputting on C, and then the output of the AND gate is then negated by the NOT gate. Right? When you look at the table of operations and you look at the output line on D, you get the same exact outputs given the same inputs. It's the 0, 1, 1, 1 pattern. Right? The thing is though is that this is only using one gate. Right, so that's the size of that circuit right there is one gate. This one is the size of 2. Okay, and also things are only passing through one gate, whereas things are passing through 2 here. Right, and so this is 100% more efficient than this. Okay, and that matters in digital circuitry when you actually have when you're working with things like electricity. Okay, and electricity produces heat, right? And it may not matter that much, but if it has to do this operation, let's say just trillions of times over, well, it's going to add up, right? And there can be an energy cost there that matters, especially in the engineering sciences. right, so I've already talked a little bit about size and depth. Let's get a nice formal understanding of size. The size of a circuit is the total number of gates in the circuit. So here you have a circuit that has 5 gates in it. And I want to mention a couple other things about circuitry design. You might take these as the input nodes. All right, and what's happening here is that, remember, electricity can go 2 different paths, right? So the input electricity that's coming this way can go this way into this gate and also go this way under this wire. So and then into this gate. Okay, so here's the thing about these little hoops, or they're bridges, I like to call them. That is a wire that's tracing along here. It hops over the other one and goes into this one. Okay, the electricity also isn't just going to this gate, it's also going down here to this one as well. All right, so you have to kind of keep track of just how that, I just want to kind of give you a heads up about how that's working, right? And so that's just a way of kind of understanding what is going on, giving you a little map. All right, so that's size, total number of gates in a circuit. Here's depth. The best way to think about depth is that it's the maximum number of gates that an initial signal, whether it be a 0 or a 1, could encounter. So in this particular circuit, it has a depth of 3 because here we're starting out, we go through that little hoop, 1, 2, and then 3, right? And you could start down, you could go this way too, right? It's going to go 1, 2, 3. And so you're never going to get greater than 3, so the answer is 3. All right, that's depth. Let's talk about how to do some of the homework problems that will be coming up. I'll talk a little bit about these in the next lecture, but the basic idea here is that you need to figure out what the output value of C is going to be, right, given the input values for each row. So this is somewhat tedious of an exercise, but it'll show you kind of how to do it. Okay, so what you need to do is take row 1 first, right? And so you have A and B. They're given to you. The information that's given to you there is we have a 1 and a 1. So look at A and B here. All right. Imagine a 1 and a 1 is starting out on A and B, and so that's going to be the input values on this AND gate right there. Okay, so there's the input values. That 1 and a 1 is going into the AND gate, and so what's it going to output? Well, given the semantics of the AND gate, it's going to output a 1. Now I draw the 1 right here because the 1 is going to go 2 different directions. It's going to go into this gate, and it's going to travel along this wire here down into this gate. All right? Okay, so let's just go this direction first. All right, and so there we have the input value on this. What's this? This is a NAND gate because it looks like an AND gate, right? But remember, it has that little tennis ball, right? Unlike the AND gate, which doesn't have that. Okay. Okay, so let's also, let's figure out what the other input value is over here. So we have to kind of go through this one first. So we have a 1. Remember, a 1 is starting out here. Right, it can go 2 different directions. It's going into this gate, and it's also going to go travel along this line, right, underneath that little bridge into a NOT gate, right? So the input value in the NOT gate is a 1, and then it's going to output a 0. So you have a 1 and a 0, right, inputting on this NAND gate, and then it's going to output a 1, which then becomes the input on this OR gate, okay? And so let's figure out, here's the little thing. If you have an OR gate and you get a 1, it's going to be a 1 right here, right? But let's just be complete for the sake of the illustration here. We're still not done. We still have this path to make sense of. This little signal is a 1. It's coming through this NOT gate. So the input value of the NOT gate then spits out a 0. And so what's happening then in the final analysis on this OR gate is you're getting a 1 and a 0, which of course then gives you a 1. Then what you have to do is you have to start the whole process over, right? You erase everything, and then you take the information here, and then you write 1, right? And then you write 0, okay? And then you just go through and do the whole analysis again, okay? Now, the depth of the circuit is 3. That's the maximum number of gates an initial signal will travel through. So there's 3, all right? You can go this way. Okay, you can go this way. It's always going to be 3. And then the size, you just count them up. 1, 2, 3, 4, 5. Okay, that's the size of the circuit. All right, so that's a homework problem that you'll have to do, okay? Let's talk about this now, all right? Let's talk about what's going on in this case. All right, so you might be thinking here, all right, how exactly, how exactly does one understand the relationship between, say, the picture that we've drawn here and this little like string of symbols here? It looks like it looks like TFL, but it's not quite, because we don't have the object and predicate distinction. What we just have is our wires being named, okay? So let's think about this, okay? What's happening here in this particular sentence, right, is we have something that looks like an exclusive OR, right? This looks like an exclusive OR, right? Because the OR is the main connective here, and so that main connective, right, is the output gate. And then the OR is connected up to two conjunctions, and so what we do is we take the wires that are inputting into the OR gate here, and we connect them up to two AND gates. Right, you kind of see how I'm doing this, right? So there's OR, okay, OR is there, right? It's connected to two ANDs, okay, there's the two ANDs, and then you gotta start wiring up. So let's look at this one first, okay? So the inputs on the conjunction here, right? We have one that goes straight to B, right? So we just link up that wire to B, and we're done. Now this A here is negated, so we gotta put a NOT gate in between the input on the AND gate and the A. And so that's why that is there, all right? Okay, the other AND gate, which is down here, notice that one of the input wires just goes straight to A, okay? And so that's what we do there. We just link it right up with A. But then we have to put a NOT gate in between the B wire and the AND gate. And so that's why that NOT gate is there. It's negating the B input, okay? And so that actually represents an exclusive OR. Now we can actually take the exclusive OR gate, right, and replace this whole jumbled mess, all right? And notice here, okay, this illustrates the idea of logical equivalence again. So this whole thing, right, is pretty big. You have six different gates. So 1, 2, 3, 4, 5, 6. Right, that's the size. The depth is 3. It's always going to be 3. Okay, and if you just take that whole mess, right, and replace it with an XOR gate, now you go down to a size of 2 and a depth of 1. And that's a massive improvement in efficiency, right? So here's the idea, right? Logical equivalence matters for efficiency because you can have the exact same output values given the same input values and yet have a smaller size and depth, right? And that's how logical equivalence helps efficiency. All right, so that's what I want to leave you with for today. Okay, that's kind of a homework question, so pay attention to that. All right, and I will talk a little bit about normal form and how we can use that to do a digital circuitry word problem in the next lecture. All right, so no practice problems today, just understand what the gates mean and understand how logical equivalence helps you with efficiency. All right, so I think if you have any questions, just let me know, and I will talk to you later.